Next up, we have a really interesting talk from Csaba and Gergely. It's really neat because when I met these researchers, they were both doing separate research, and so it's really great to see them jointly come together to give a talk on something that I think is going to be a really cool vulnerability. So, round of applause.
Hello, welcome everyone. This is Crash One, StarBucks story. I'm Gergely. I'm an independent bug hunter. I used to do a lot of development and sysadmin stuff. I found a bunch of 0 days on macOS, and that's basically the focus of my research, and you can find more on the URL below.
My name is Csaba. I'm working as a macOS security researcher at Kanji, mostly doing vulnerability research and detection engineering. I used to work for OffSec, writing a macOS exploitation training. I do hunt a lot of macOS bugs, right now over 100 CVs, and I'm really into trail running, hiking. I'm the one organizing the OBTS 10K tomorrow, so reach out if you are interested. So we have a lot to talk about. This is a very packed agenda, so let's start. It's called StarBucks. They didn't support this talk, unfortunately, although if they want, we are here for the free coffee. So how it all started. About a year ago, Gergely visited in Hungary, and we sit down, and where IT people sit down, of course, in a StarBucks. So we sit down, shared some research ideas where we stuck, and talked through some ideas, and eventually we were talking about a bug, a potential vulnerability that both of us found, but both of us found it non-exploitable that time, because we hit a wall with that vulnerability or potential vulnerability. So what was that? That was the osanalyticshelper daemon. This is a helper daemon process which is involved in writing out crash reports. So if the process is running as the user, then the crash report is being written out into the user's home directory, diagnostic reports, and if the process is running as root, then it's being written to the same directory, but under the root. And the issue we found, or we thought that it's problematic, is that this helper daemon is running as root, and when it writes out a crash report for a user-owned process, it touches a directory, the diagnostic reports, which is owned by the user, accessible for the user. So the user have the potential to mess around with that file write. If you see the file system events, we saw that it opened the directory, it basically created the crash file, it changed its ownership to the user because by default it's root, it did a chmod, making it read-writable, and at the very end it renamed the file from basically deleting the leading dot from the file name. But what were the problems? Well, the first one in the list wasn't really a problem, but still an interesting behavior. The daemon checked if the directory is a symlink. And we expected if it's a symlink, it will error out, but it didn't actually, just moved on. We are not sure why the check is there. Maybe it's a wrong check, but anyhow. Then it used the oxl and ocreate flags with opening the file, which means if the file is not, if the file exists, it won't be created. So you cannot place like a symlink or hard link before the file is actually created, because this will fail. But the biggest hurdle was the sandbox profile of this helper daemon, which basically restricted its access anywhere on the file system. So it really could only write to these two locations. So yeah, just messing around, we didn't really get anywhere. But eventually we checked again the sandbox profile of this application, and it turned out we both of us missed something. This is the one thing we missed, and this was a crucial step in the entire process. So the sandbox profile contained these two lines saying that if the process has a sandbox extension called com-apple osanalytics sandbox read-write, then it can read and write any file on, basically. But it's tied to this extension. So what is a sandbox extension? Now, in a form, it's a C string, it's a signed token, but basically on a high level, it was created to extend the process sandbox or access beyond its current sandbox environment. So typically, it's being used for adding access to services, to file, to a certain process. So the way it usually works, we have two processes. One is unsandboxed and let's say privileged, and there is another one, which is the sandbox one. So process A, which has access to the file, creates a token, a sandbox extension, send it to process B over XPC or whatever method. Process B has to consume the token. This is a crucial step because if process B doesn't consume the token, then it doesn't come into effect. So process B consumes the token. It can eventually release it as well, but basically this is how process B gets access. This is the Apple API. To use this, we can issue token to files, services, etc., and we can also consume it. So what we did, we said, okay, let's create a token. We will create a token for the root file system, which means it gives you access to every single file. We will set the sandbox extension to the specified string, and we will send it to osanalyticshelper D, and we will hope it will consume it. Again, consuming is a crucial step, so we were after like, okay, even if I send the token to osanalyticshelper, how do I ensure that it will actually consume it? So it had a function called OSA sandbox consume extension, and sure enough, it had the standard API to consume the extension. Now, this function was called from a huge function, which is basically an XPC handler inside this process. The XPC handler was like a massive function, like multiple hundreds of decompiled lines, lots of entries, and we were like, okay, this is really tedious to reverse. So what we did, okay, let's just attach to the process, crash something, and see what is the actual message. So this was the message, short one. Again, I'm lazy. I just took this message, pasted it to ChatGPT, and said, okay, create me the C code that will create this message. So the plan was, is we create a token, we send it to osanalyticshelper to this XPC message, hope that it will consume it, and basically we wanted to create a crash file somewhere. Now we badly failed at step 3. Eventually the token was consumed because that's like under normal operation. It does consume it, but the crash file was not created. We got some weird back channel errors. So what was that? There was a function to handle some back channel, and we noticed that this back channel is basically a callback over XPC to the original process calling osanalyticshelper D. So after some reversing, turned out that what's the real purpose of this back channel? So under normal conditions, report crash daemon will call osanalyticshelper D over XPC to create a crash log, and osanalyticshelper D will create the log file, open a file descriptor, and send it back to report crash to populate the crash information with more info like VM map, stack trace, etc. And report crash has to return with 1, because if it's not, then the crash file will be deleted and will not be created. So what we did, we had to simulate this behavior. So in our exploit code, we created an anonymous XPC endpoint, and we handled this callback and returned 1, and the file was created. So what we could do is basically at this stage, we could create a token and create a crash file anywhere on the file system, but we didn't control the content, etc., so we moved on.
Right. So now that Csaba has done all that hard work, we end up with something like this, which might be familiar to you. So this is the output of a tool called fs_usage. On the Mac, it comes on the system by default. So what it doesn't show you is that the rename actually takes 2 parameters. This is the first parameter. The second parameter is basically the same, except with the dot removed. So this is an in-place rename. You might have heard me talk about this before. So this is essentially equivalent to the example above. Basically, you just change the file's name, but the path stays the same. Now, most people would assume that this is fine, and I was one of those people before I dove into this research. So you think because of the kernel is going to be clever, it's going to be caching, and as it turns out, it's going to do none of those things. And if you've been following my work a little bit, you know that what's about to happen is, because whenever I see this, I immediately abandon everything else. And the reason I do that is because this is a massive pitfall. So this is actually a race. So in any system call, rename src and dst, the kernel will look up src and dst separately. And it has to do that, because if it doesn't, things might change in the meantime while you're in the system call. And that is perfectly POSIX behavior. That is how it's supposed to work. So it's kind of a feature, really. But for us attackers, this is tremendously, tremendously useful. And not a lot of people know about this. So every rename is racy, so yeah, have fun with that. I found 0 days with this before, and there are basically two, I would say, prerequisites, but the second one is a nice to have in certain situations. So the first one is that you have to be able to control one of these paths to begin with. Since the paths are the same, controlling one controls the other, so we're pretty much fine here. But we do not control, we do not control the destination file name in the destination parameter, which, kind of sucks. So, however, do notice that our target does run as root, and that's going to help us a little bit. So, to win a race like this, you can be clever or you can be brute forcing. And I'm not very clever. I tried to do that route, and it didn't quite work well. So, in order to brute force, it's always more portable, easier. You can just fine-tune parameters as you wish, and it doesn't require a lot of work, so it's easy to prototype. Basically, two things you need here. One is that the race itself has no serious side effect, i.e. this includes that you can try again and again and again and again. And that the race itself is quick to run, unless you're willing to wait for, I don't know, months, but most of us don't. So both is true in our case, so this is a prime target for brute forcing. Basically, brute forcing means you just swap the parent directory with a symlink in a loop, atomically, and eventually there are 4 conditions that can be, or like 4 situations that can come through here. The winning condition is this one, where the original file is taken from the original location, but the destination file is at the path that we control. Notice how we completely control X, we do not control Y. And this is an almost fully controlled file override, because we do control everything about the file. However, the name does not belong to the file. I know, it's a bit counterintuitive. But the name actually belongs to the directory that the file is in. But we do control the inode, we do control the permissions, the content, everything, basically. So very powerful primitive, but lack of file name control still sucks. So we have to weaponize this somehow. And how do you turn a file write like this into privilege escalation? Well, you can use the classic tricks. You can try to override scripts and whatever, but file name control is gonna screw you. And this is also Mac OS, so the classical Unix Linux tricks don't really work well. Cross TCC protected, there was something else there. But there are a couple of system services, and in particular sudo is very, very helpful, because, so generally speaking, any *.d directory under etc would work very well, because the file names do not matter here. So we ended up attacking sudo via etc/sudoers.d. There are 2 things that sudo needs, really. That the file is, according to the basic Unix ownership, is owned by root, and the permissions are restricted, i.e. the file is not world writable, because that would be pretty bad. We can solve this any number of ways, but I chose ACLs, because ACLs are pure awesomeness. They're really good because there's no racing required, and they're very flexible because the ACL is a permission that stays on the inode, so wherever the inode moves, the ACL moves with it. If you do not know what those are, you can always check the man page. Haha, jokes aside, let's do a little quick speedrun if we have time. So this is actually a draft. This is standard. That got revoked. Good luck with that. It got implemented on Linux and BSD, which is basically macOS anyhow, and these are not compatible. So yeah, terrific. On macOS, this allows us to have inheriting ACL. So in the example above, you see that the attacker user is given access over mydir, and one of these, 2 of these accesses is file inherit and directory inherit. So whatever gets placed into this directory by whoever is going to have the ACL put on it, so that whenever that file moves out of there, I still have control. So this sounds like a backdoor, because it kind of is. So you need to call a libc function to even check whether this is the case. Now, most programs don't do this, and good luck upstreaming a change that will check for this, because this is implementation, or operating system dependent. So you have to if-def all that, you're never gonna get that merged. Sudo is one of those. So that gets rid of our problem. Basically, there's another issue, minor issue, that osanalyticshelper would set the owner. And again, we could have bypassed this, but it was much easier. Csaba just found that if you set this particular variable to 0, it will not do that. So I put it all together, you know the drill, yada yada. We basically had an exploit where that actually did the hard work of being the XPC client, invoking all this, handling the Sandbox extension stuff, handling the callback, and I wrote some wrapper around it in Python that prepared the environment and just basically hammered the system to crap with this. And meanwhile I did that, I tried to raise the rename, detected success, and then that's it. That was basically the whole exploit. This is how it looks. So we check for the version, we check whether we can sudo without a password, and it's not going to work, and we run the exploit. So this is actually sped up a little bit. I think the actual exploit runs in like a minute or two. We could have sped that up, fine-tuned it a little bit, but this is only for Apple. We're not weaponizing stuff actually. So, okay, there we go. So we succeeded. So this works now. Yeah. So, yeah, this is your point.
Yeah, so why stop with an LP if we can do more? So we were like, okay, can we do more with this trick? And we're like, can we escape the sandbox with this? Now, this will be short. So escaping the sandbox with this trick was a bit constrained. First, only platform binaries had access to this XPC service, which is still great because any Safari, screensaver, everything could still access this service, not like the generic third-party Sandbox application. Now, from the Sandbox, you cannot issue a Sandbox extension, so that will not work. But osanalyticshelper can still access the library logs diagnostic reports directory, and we were not after like LP in this case, but just Sandbox escape. And the idea is that we create some file which doesn't have the quarantine attribute. Now, Sandbox macOS application don't put the quarantine attribute on anything, thank you. So we can utilize that. So the idea was that we use the osanalyticshelper to drop a DMG file. Actually, we found out that through the XPC connection, we can fully control the file name. So we could place like a test DMG. And through the back channel, if you remember, we got back the file descriptor, so we could fully override the content of that file. So we basically just jumped to the beginning of the file and put the entire disk image into the file. So we managed to write out a disk image into diagnostic reports. Why is it good for us? It doesn't have the quarantine flag, so we can just open the DMG, like run open and the pass. That will be auto-mounted by the system, and since the DMG file didn't have quarantine attribute, it will be mounted unquarantined. We placed an application, an unsandbox application on the DMG, and just run that file. So that was the sandbox escape part, and the application we placed there, of course, was our LPE. Now, so we basically chained together the two things, first escaping the sandbox, and then getting root. And so since its sandbox escape is only available for system processes, we couldn't just do like a third-party sandbox app, so we decided, okay, we will do a screensaver. Screensaver is loaded, it's actually a dilib. It will be loaded by the screensaver daemon, which is heavily sandboxed. But since it's a platform binary, it can access the XPC service. And eventually we made like a reverse share back to another machine. So we installed the screensaver. You don't really need to run the screensaver. You just scroll to it, click on it, and basically at that stage it's already executed. We can see that the disk is mounted with our exploit app. Now the application is running, and this exploit application is actually running, doing the same what we saw in our previous step. And we got back a reverse shell as a root.
Right. So this is one of the rare cases where Apple actually managed to roll out a fix for the first time and it was perfect. And not only that, And not only that, no, I know they have a lot on their plates, obviously, but so now this is all entitlement gated, so we can't call it at all. And if that wasn't enough, they actually fixed the rename vector, so they just like did defense and depth very properly. Good job, Apple. That was the actual correct fix. And I guess we're gonna do this hopefully next year.
Yeah, so I said last year that I plan to do a training on vulnerability research sometime in the future, and Gergely wanted to do something similar, so we decided not to compete with each other, but to team up. And so we will actually do this next year. We don't know where yet, but yeah, it's being done actually.
Yes. Thank you very much.